natural numbers and integers, and certain additive or arithmetic properties of those. Let me get started. So let's just first say what are the basic objects. All right, so we have the natural numbers. Oh, by the way, I should say that please feel free to interrupt me to ask questions. So these are just the numbers which we learn in elementary school, 1, 2, 3, 4, and so on and so forth. Okay, then we can also extend this number system to the next larger number system, which we also learn already in elementary school. These are the integers. And they consist, let's write them this way. Okay, so we have also here negative numbers. And there is a basic operation defined on these numbers, which is addition. We have also multiplication. And this is what it means to have arithmetic. Okay, so these are called arithmetic operations. All right. So now, in terms of mathematics, these operations of addition and multiplication satisfy certain properties. For instance, if we take two natural numbers, say n and m, we can add them together and we get another natural number. And somehow it doesn't matter if we first add m to n or we add m to n. Okay, there seems to be already a question. So here we exclude 0 from the natural numbers, but you can also consider 0 as a natural number. Okay, it's yeah, it depends on the context. All right, so we can, and then there are some other laws. So we know, for instance, if we add two natural numbers, say like this, then this is the same as adding the first two and then adding a third. So the first property is known as commutativity. The second property is known as associativity. And as one participant pointed out in the chat, if we have a 0, then we can also add 0 and we get the same number. So 0 is sometimes called the additive identity. Okay, so these are fancy names for very elementary things which we learn already in elementary school. We just call them a little bit more fancy. Okay, so to sum up, mathematically, the natural numbers with addition is a semigroup. Basically, it summarizes these laws which I said. And in the case of integers, actually, this is a group. And this is a commutative semigroup. In the case of integers, this is a group. So what does it mean? What makes a distinction between the integers and the natural numbers is that for all natural numbers, for all n in z, so there is minus n, okay, also in z, such that n plus minus n is equal to 0. Okay, so there exists.
Can I ask a question?
Yeah, sure.
Could you please define what does it mean being a semigroup?
So basically what I just wrote here. So it means that you have this associativity law with respect to this operation which we just defined.
Okay, thank you.
Okay, so this is just a fancy name for saying that the natural numbers with addition satisfies the associativity law. And it is a commutative semigroup because one can also swap the addition, okay? So it is actually for this talk not so much important. I just wanted to throw in a couple of words so that because I will need some terminology when I go ahead, okay? But actually, it is not so much. It's not so important that you for the whole talk. Okay. So and this guy is called then inverse, and this is an additive inverse. All right. So group here. So a group here means that we have these properties. Okay, a commutative group. This is also a commutative. So we have commutativity, we have associativity, we have an additive identity, and we have also an additive inverse for every element. Okay, an inverse is just meaning that there is a unique element such that if I add them together, I get the additive identity. Okay. All right. So this means that these two very basic objects have some additive structure. They have some arithmetic structure, and this arithmetic structure is somehow well behaved. Okay, this is basically what these properties are saying to us. But there are also so we can now, what we would like to understand is if we choose some subset, I will say what this is. So for instance, if we choose a collection of the natural numbers, usually this is written in mathematical notation as this. So this is a subset. So a subset just means that we choose some collection of the natural numbers, okay? So that could be, for instance, all even numbers is a subset, or all odd numbers is a subset, or all multiples of 3 is a subset, okay? Or, I don't know, all numbers larger than 200,000, that is a subset, okay? So this is just some sub-collection of all the natural numbers. And the question we are interested in is that if we pick a subset, how can we decide if this subset has some arithmetic structure? Okay, so we pick some subset of natural numbers and we would like to say something or decide whether the subset, which we maybe even pick in some random way, okay, has arithmetic structure. So what do we mean by this? Arithmetic structure. So let's discuss some examples of arithmetic structure. So for example, take all the even numbers. I write them in this way, 2 times n. Okay, these are all, this is a collection of all even numbers. Then this even numbers, they have some arithmetic structure because if I, or additive structure, because if I add 2 even numbers, I get another even number. Okay, so if I have 2 numbers, 2 times n, say, plus 2 times m, then this is 2 times n plus m, and this is again even. So that means that somehow the even numbers are additively closed. Okay, the same thing I can say about all multiples of 3, or more generally, I can say the same about all multiples of some natural number m. Okay, where, okay, I should maybe not use too much mathematical notation. So m here is an arbitrary natural number. Okay, So this means that these sub-collections, they are quite structured. Okay, but the question is, can we also say something about other sub-collections? Okay, so for instance, another sub-collection which, by the way, let me also add this. So if you, instead of the natural numbers, consider the integers, then in fact, m times the integers, okay, will be also a subgroup. So that means that it will satisfy all these properties of a group, which we had here. Commutativity, associativity, having an identity element and an additive inverse. Okay, so it is basically has a lot of structure, additive structure. Okay, so in the case of integers, that's just as a side remark. But okay, these are the very obvious objects. Okay, so the question is, are there some other like subsets or collections of numbers which also have arithmetic structure, and how can we find them? So now the thing is that maybe we have to relax a little bit our notion of arithmetic structure. So here is an example of another arithmetic structure, which is called in the literature as arithmetic progressions. So what is an arithmetic progression? So before I introduce finite arithmetic progressions, look at the following numbers. So we take the even numbers and we add to each even number 5. Okay, so what do we do? So we start with 7, 9, 11, 13, and so on and so forth. Okay, so we add to each even number 5. Okay, so now, of course, this property that two numbers of this form, say 2n plus 5 and 2m plus 5, if you add them together, they will not again be a number of this form. Okay, so this means that this is not really again something a subgroup like object or a sub-semigroup like object, but still it has some arithmetic structure because the difference between each two elements, okay, is an even number. Okay, so that means that there is some arithmetic or linear, or if you are a little bit familiar with mathematics, it has some affine structure. Okay. For those who are not mathematicians here, forget about affine. So what it just says, it says there is still some arithmetic structure hidden in that guy. But now what we can also do is that instead of looking, so this is an infinite progression. So there are infinitely many numbers such that each two consecutive numbers have the same difference, here namely the difference 2. But let's also relax a little bit our understanding of arithmetic structure and just consider finite such objects. For example, let's consider the following: 9, 13, 17, and 21. Okay, so what are these numbers? So this number is 4 plus 5. Sorry, I want to write it differently. This is 5 plus 4, 5 plus 2, 4, 5 plus 3, 4, 5 plus 4 times 4. Okay. So in general, so this is called an arithmetic progression. Okay. That's a finite arithmetic progression. So, and the defining property is that there are finitely many numbers such that the difference between two consecutive terms is always constant. So in this case, it is always 4. More generally, we can write this as follows: a plus, so you have some number with which you start, say A, and then you have A plus B, A plus 2B, and so on and so forth. And then you have A plus, say, KB. Okay, so this is not quite a sub-semigroup or a subgroup or whatsoever, but it is still an object which has some additive structure. Okay, some arithmetic structure. Okay, but somehow not globally like this guy, where you have an infinite thing, or this guy. Okay, but it is more in local additive structure. Okay, but still it is structure. It is something, it is a pattern. Okay, speaking. So it is a pattern which has something to do with just a very basic operation of addition. Okay, so let's introduce some terminology here, which we will need. So we call such a progression an arithmetic progression of length k plus 1, because it has k plus 1 many elements. Okay, so this is 1, 2 until k, and then there is this initial one that makes it k plus 1. Okay, and step size b. Okay, step size here means the so how much we move each time forward. Okay, so now we can rephrase our question, which we had at the beginning. So we want to find this type of structures in collections of natural numbers, and we want to somehow classify those objects which contain this kind of additive structures. Okay, we want to classify like so let's again rephrase so that's actually the title of the talk, where to find arithmetic progressions. Okay, so you take a subset. So again, a subset is some collection of numbers. Okay, and the question is, can we decide if A contains arithmetic progressions? So some form, in other words, some form of additive structure. Okay, so how can we decide this? So the thing is that A could be anything, right? So a priori, we don't know, so we don't impose anything on A other than being some collection of numbers. Okay, so maybe I should stop at this point and see if there are any questions before I go to the next. Okay, this doesn't seem to be the case. So here is an example of a subset which you probably all are familiar with. Suppose A are the primes. So A is a collection of all prime numbers. Okay, so these are numbers larger than 2, such that they can be only divided by themselves or 1. Okay, these are somehow the atoms of all numbers. Okay, so if you do number theory or if you do mathematics, then the primes are the atoms of all numbers, because you can write any number as any composite number. Okay, so any number can be written as a product of powers of primes. Okay, so the question now is, the primes do not have any, in fact, since several thousand years we try to understand them, and yet we don't know much about them. They don't seem to have any obvious structure. Okay, so the only structure that they have, and the only thing we know about them algebraically, is that they somehow generate all the numbers. Okay, So the question is, A could be, for instance, the primes, and then now we want to but find structure in primes, because the more we want to understand the primes, the better it is, okay? Because they somehow build up our number system. So a question we could ask, so one type of structure is additive structure. I mean, the primes are only defined through multiplication, okay? These are the atoms of all numbers with respect to another arithmetic operation, namely multiplication. But we could ask the questions, do the prime have some additive structure? Meaning, do the primes, for instance, contain arithmetic progressions? Okay. And that is an absolutely not trivial question. And it could be only answered in 2006. Okay, I'll come to that later. So in fact, 2004, I think the paper was, and it was accepted in 2006. I should be careful. Okay, so we should, it is a very new field of mathematics. What is a new field of mathematics? Number theory. Number theory is the oldest field of mathematics. It's not particularly new, but the questions we have, some of the questions we have are very old and we cannot answer them. Like, for instance, if there are infinitely many twin primes, for example, or stuff like that. But combinatorial number theory, so the type of number theory so basically what I will talk about is, that's right, that's quite recent. So I think it is maybe somehow 100 years old or a little bit more. And there has been particularly a lot of activity in the past 50 years or 40 years or so. Anyway, so these are, for instance, some form of subsets we would be interested in. But before talking about the prime numbers, let's go to some general subsets of the natural numbers. So one way to, so if you take some arbitrary subset of the natural numbers, so that means some arbitrary collection of numbers, then one way to classify or to describe it is the size of that set. So the size of that set in mathematics called the cardinality is meaning how many numbers are in that set. Okay, so for instance, if you choose A to be, I don't know, 1, 2, 3, then this set has size 3 because it contains exactly 3 many elements. Okay, so one way we could ask is that, so one obvious, or one, let's say, one first criteria one would think about is that if you choose a certain subset which has a certain size, so it is like, I don't know, it has 200,000 elements. We don't know what the elements are, we just know that there are 200,000 elements inside it. Can we say something about if a 200,000 many elements have some form of additive structure? Okay, so that would be one way to approach this question. So I want to now show you, okay, maybe I should rephrase. So there are several notions of, so one is size, and size can be measured in two ways, or in several, actually in many ways. But one way we want to do at the beginning is that just the number of elements. But then there is another way to measure this, and this is called density. I will come to this later. Okay, because infinite sets, if you have an infinite set of numbers, then for instance, 2 times n, okay, so all even numbers, there are infinitely many of them. Okay, then the size will always be infinite. But we will see that even among infinite sets of numbers, there are differences. Okay, some infinite set of numbers will have arithmetic structures, others will not. And we will again find a notion or find a way how to detect those infinite sets which have arithmetic structures and those which don't. Well, those which don't is a bit difficult, but those which have, we have some criteria to decide that. Okay, but for the moment, just consider like finite sets. So this means sets which have only finitely many numbers. Okay, like 100 or 200 or 3,000,007, for example. Okay, so now, but we can start also like this. We can, we can also turn this question. Okay, in order to, we can also ask the inverse question. We can ask, which is actually somehow a reformulation of the same question. Can we construct sets which lack arithmetic structures? Okay, so this is just the same question, but so this is again the same question, just asked differently. So if we can characterize those sets which have arithmetic structures, one can also ask, can we like find those? So this is another way to say the same question. Can we like you negate this question? Can we also we can also study those sets which do not have arithmetic structure, and by understanding those sets, then we know for which type of sets we should look for which have arithmetic structures. Okay, so this is an exclusion principle. Okay, so that's also a way to approach this question, and I want to show you now an example of how to try to avoid arithmetic structure but ending up finding arithmetic structure. Okay. So suppose you start with just the first numbers, 1. So what I want to do is that I want to avoid finding a 3-term progression. Okay. So a 3-term progression. So a 3-term progression are just 3 numbers, such as 2, 4, and 6. Okay, so which are the same amount apart from each other. Okay, another way to characterize 3-term progressions, these are solutions to the following equation: a plus b equal to 2c. Okay. Any 3 numbers which solve this equation will form a 3-term progression. Okay, so another way, we want to construct a set which avoids solutions to this set. Okay, so now let's start with the first number. Okay, this is 1. Okay, so we can, without getting worried, we can add 2 to the, I think I lost connection with my iPad. Sorry. Unfortunately, this happens sometimes with the connection here. Okay. So unfortunately, in my office, the Wi-Fi is sometimes weak. Okay. So can you see my screen again?
Yes, now it's okay.
Okay. All right. So we want to avoid having progressions, 3-term progressions. Okay. So, and we start at the beginning of all numbers. So we can take 1. If we take 2 into our set, okay, it seems that I got again lost. Let's okay, maybe I should move a bit. Sorry for that. Okay, so I hope it will be better now. Okay, so for the third time, let's start again. So we start with we try to avoid 3-term progressions. So we can take 1, and then we can 2. So 1 and 2, of course, doesn't form a 3-term progressions because these are just 2 numbers. Okay. So, but now if you would take 3, then we would have a 3-term progression where the gap size is just 1. Okay, so we have to throw away 3. Okay, so we don't take 3 into our set. But then we can take 4, right? Because 1, 2, and 4 doesn't form an arithmetic progression. Right? Okay. So can we take 5 into our set? Yes or no?
I think yes.
Yes. So you can take 5. Also taking 5, it doesn't give you an arithmetic progression. But again, you cannot take 6. Okay, because if you would take 6, then 2, 4, and 6 would form a 3-term progression, which is written there. Okay, you can also not take 7. Because 7, 1, 4, and 7 would form a 3-term progression. Okay. All right, so you cannot take 7, but you can take 8. Okay. But now comes the following funny thing is that now is that you, in fact, what I want to say is that, so if you now don't take 9, okay, so you cannot take 9, because if you take 9, then you would have an arithmetic progression. Let's see, you would have 9. So you would have 1, 5, and 9. 2, 5, and 8 are a progression.
Teacher, we have a comment in the chat.
Yeah, wait. 2, 5, 8 is a progression. That's right. I did a 2, 5, and 8 is a progression. So I cannot take 8. Okay, this thing already breaks down at 8. That's fine. Just want to illustrate another point. So this breaks down as 8. I cannot take 8. And the thing is that I cannot also take 9 because we would have 1, 5, and 9. However, so just look at the size of this block. So this block has exactly 9 elements. Okay, so and we split it into 2 parts, this 9 elements. Okay, those parts which we took in our set. Okay, this is 1, 2, 3, 4, and those which we didn't take. Okay, these are which are circled. But now if you look at the circles, you will find several arithmetic progressions. This is 1 and this is 1. That is, we could not avoid already in the first 9 numbers. Okay, we could not avoid splitting this into 2 sets such that none of them has a 3-term arithmetic progression. And in fact, you can prove this. Okay, let me show it to you. So you take, so these are the ways So these are the ways you can split. Let me see if there is a question. Oh, no. Okay, so these are the ways you can split or color the first 8 numbers into 2 colors, such that these 8 numbers do not have like in one color, you have like a 3-term arithmetic progression. Okay, so this coloring here does not have a 3-term arithmetic progression. Okay, but if you add one color, whatever, so you split this basically into 2 sets, but if you take this element into account into one set, so you color it, let's say red, then you will have a 3-term progression here. So for this collection, if you color this one blue, then you will have a 3-term progression here. And now all the other 2 colorings of 8 numbers, okay, which avoid a 3-term progression are listed here. So you can just check this through. This is like just a combinatorial exercise, which is rather elementary. You just try to split the first 8 numbers into 2 collections such that none of them has a 3-term progression. And these are all the possibilities, these 7 possibilities. But in each of the 7 possibilities, whatever you color the 9th color, okay, either blue or red, it will always form a 3-term progression. Or in other words, is that you cannot color, so you cannot split the first 9 numbers into 2 groups such that none of these 2 groups have a 3-term progression. That's actually quite interesting because splitting numbers into 2 sets is a purely, can be done in a random way. But then the result will be that you cannot avoid additive structure. Okay, so so you can try this yourself out. This is you can just try it out. You cannot split. So let me write this as a sentence. You cannot split the first 9 numbers into 2 groups such that both groups don't contain a 3-term progression. Okay, so this already tells us something. So this already tells us something how we could find progressions in sets. Okay, so there is a relation between size apparently, namely 9. Okay, and between additive structure, namely here 3-term progressions. Okay, if you want to look for longer progressions, say 4-term progressions, you need to look at longer strings. But for each progression, these are called, for each progression, there is a finite number of elements which you can take, such that you split them into 2 groups, such that one of these groups will contain, say, a k-term progression. Okay, so what does it say? So this says that you cannot destroy arithmetic structure, you cannot destroy the additive structure of the natural numbers, okay, by just splitting sets. Okay, and actually, in fact, this is a theorem. A theorem in mathematics is just a statement which is true, like a physical law or something. Okay, so which we can prove, and this is actually a rather basic result in this area, and this says the following, and it is due to Funda. It's called the Funda theorem, and it says the following: if you take the natural numbers and you split them in finitely many pieces. So let's write it this way. I will explain what this means. A2, so these are mathematical symbols, but what you can imagine it as follows: take n many colors, take n many colors and color all numbers by one of these colors. Okay, so you color all the numbers by n many colors, for instance, 3 many colors or 2 many colors, say just blue and red for simplicity. But you can choose any finitely many colors. And now Funda theorem will tell you that there is for all k, so for every k, there is some color. There is some color such that you will find a k-term arithmetic progression in this color. Okay, so that means that however you split your whatever do you do for a splitting. In fact, this is a quite strong statement, because you can not only find 3-term progressions, you can find progressions, arithmetic progressions of any length. And in fact, you can find infinitely many arithmetic progressions in any length, which are in one of these classes. Okay, so that means that somehow just by splitting the natural numbers into different sets or color them or do some operations, you cannot avoid destroying the additive structure of the natural numbers. Okay, the proof of this result is not so easy, and it is like a combination. There are several proofs of this. I will not go into that because this is like a general audience talk, but there are many ways to prove it. And originally it was proven by a very clever combinatorial argument, but which is by itself quite lengthy. Okay, it's not a simple combinatorial argument. You need to like do something clever, and it takes a couple of pages to do that. All right, so let me see what is the time now. Okay, so maybe so now, but you could ask, okay, so you say, okay, fair enough, I cannot split, but there are subsets where I can avoid 3-term progressions. Okay, so for example, if I would do the following. So you take the first number, say 1, and then you take a gap of 2. Okay, so this is like 2 and 3, and then you take 4. Okay, and then you don't take a gap of 4. Okay, and then you take the next number. What should it be? So this is 2, 4, 8, 9. And then you take not the next 8. Okay, and you continue this way. Okay, so you take one number and then you take not 2 to the n many numbers you don't take. Okay, so basically you jump, and each time you jump by the double, you double your jump lengths. Okay, and you take only those numbers where you jump up in. Now you can check that if you do this infinitely many, often you get infinitely many numbers, but this infinitely many numbers, there are no 3-term progressions by construction. Okay, but somehow if you look at this set is quite sparse. Sparse meaning it hasn't too many elements, because the gaps are very large. If you continue, right? If you, this is exponential, right? From the pandemic, we all know what is exponential growth. Okay, so these gaps, they double exponentially. Okay, so these gaps become humongously large after already very few. Okay, so very few steps. That means that you are taking very little actually of the natural numbers. And very little, one can say it is very sparse. There are very few elements which you take out. Okay, so this leads to another natural question, which is if I do not take sparse sets, so the contrary to sparse is dense. So I will define what it means. So if I take dense many sets, can I always find arithmetic progressions inside them? So let's see what this means. So one way to capture this notion is as follows. You take again a subset of the natural numbers, okay? So this is some, again, some collection of numbers you choose, and choose infinitely many of them. Okay, you choose just infinitely many numbers. And now you can look at the following quantity. You intersect, okay, I will write it and then explain it, what it means. So what does this quantity mean here? You look at the proportion of A in the first n numbers. Okay, so you take your set of infinitely many numbers, you look how many of these numbers are less than n, and you divide it by n. So basically this just means the proportion of this set in the first n numbers. Okay, so that's a proportion of this set. So for example, you can, I don't know, if you take, for instance, n to be 2 times all the even numbers, okay, then the proportion will just be n over 2, okay, divided by n. So the proportion will be 1/2, okay. So now you take any set, you look at the proportion of it in the first n numbers, but now what you want to do, you make this n larger and larger and larger and larger and larger. Okay, so you look at the asymptotic proportion of your set in finite chunks of the natural numbers. And let's assume that as n becomes larger and larger and larger and larger and larger, you still will have a positive proportion of elements. For instance, the even numbers, they always will have 1/2 density, regardless of what n is. So that means that actually they have a density of 1/2 inside the natural numbers. Okay, and a way to measure this density is this proportion. So you let, as mathematician would say, let n go to infinity, and then you look if this proportion is something positive. Okay, for instance, the even numbers have such a positive proportion. And then the question you wanna, so if, and this is called a positive dense set, okay? And now comes a funny observation, and this says the following, and this is now a result of ready, oh, like this maybe. That whenever A is dense, in the sense we just give it to it, then A again contains infinitely many k-term progressions, k-term progressions for any k. So that's somehow funny. So that just means that as long as your set is somehow dense enough, then automatically it will contain a lot of arithmetic structure. Okay, and this result, by the way, is stronger of the results which we had before. Okay, so that means that somehow arithmetic structure gets lost if your set is very sparse. Okay, so the question is this the end of the story? Okay, so did we now fully characterize all sets which have arithmetic structure? So we know that now then So we know that if we color in finite, so if we split the natural numbers in finitely many pieces, then there will be one piece which has arithmetic structure, or we can somehow, if we take sets which are very dense, they will contain arithmetic structure. But the question is this the end of the story? It is not the end of the story. So in fact, the primes are not dense. To prove this is not so easy, but you can just believe me for the moment. So this follows, for those who do mathematics here, this follows from the prime number theorem. The primes have a density which is asymptotically of this form. Okay, so the density of the primes is something like this, n over log n. Okay. And so this means that the number of primes below n, okay, are of this size. So if you take the reciprocal, if you divide this by n, then this will go to 0. So the primes are not dense, but there is a famous result, as I said at the beginning, which says that also the primes contain arithmetic progressions. Okay, so, and maybe I see that I am already almost reaching the end, and I wanted to just give you an open problem. I hope I could motivate it somehow. So there is so as I said, this is not the end of the story. So there is an open problem. So open problems are called conjectures in mathematics. So what is a conjecture? So a conjecture in mathematics is like a hypothesis or a strong hypothesis in physics, or I don't know, in other areas. So it's basically something which many mathematicians who are experts in the area believe to be true, but nobody can prove it. And it is unproven since at least 50 years. Then you start to call it a conjecture. Okay. And so here is a conjecture, and the conjecture says the following. If you take a set inside the natural numbers such that it has density, asymptotic density of this form. Larger than that. So what it means, it is, so it should have, okay, this is, so I will try to explain this. So the proportion of A, or the number of A in the first n elements, okay, should be somehow asymptotically larger than this quantity here, n over log n to the power 1 plus c, and c is a positive number. Okay, so this does not mean that it has positive density, but it just means that it has barely so positive density. Okay, it has maybe density 0, but still it has a considerable growth, and the growth is with respect to this function. Then A should have lots of arithmetic structure. In particular, this would imply the result for the prime numbers, but this is open. And maybe I end here.
Okay, thank you, Hocam. If you have any questions, now we can ask our teacher.
Oh, sorry.
So apparently we have no questions, teacher. So we want to thank you again, and thank you for all participants. Okay, no. 1 minute. There is one question. Okay, now 1 minute. Okay, the question is, do you expect the final conjecture to be proven in near future?
So recently this has been proven, the conjecture has been proven for 3-term progressions, but the general case is open, and it was just last year. But for arbitrary, and the techniques used there will not suffice to prove the conjecture in general. So to prove this conjecture, one needs a new technology. And this technology, I don't think that it is too far away, but I also don't think that it is like, I don't know. I don't think that someone in the next 6 months will come up with a solution, but I don't know. But I don't think that it is very, very far away, but it is but also I don't think that it is easy. There is substantial amount of new input needs to go into the general proof. And I think our understanding from the overview which I have, our understanding is still quite a bit away from that. I mean, already if you look at the 3-term case, the 3-term case has been open now for almost 100 years. And it was successively solved, like first by Ross in 54, and then they were improving the bounds over like almost 60 years until they reached the final conclusion. And the 3-term case, we know which kind of techniques we can use. So just to judge from that, and a lot of very good mathematicians worked on that questions. So there has to be some genuinely new insight into the subject, in particular on the technological side, which should allow to, yeah. So if I would give a guess, then I say that at least 10 years away from now, but maybe also 200, I don't know. But maybe one of you can solve it, I don't know.
Okay, if there is another question, you can ask. So it seems that's all, teacher. So again, thank you for your contribution to this event, and thank you to all participants. So, we hope to see you in next day events. So goodbye, everyone.